In this video, we are going to talk about differentiation of functions with multiple variables. This is one of very few videos I have that actually have 2 pages of overview. I really like to fit all of my topics on one page, and I did squeeze it in on one page, but I had to get rid of examples and everything was really cluttered, so it's just going to have to be this way on 2 pages. So let's get started. First, since we have a function of several variables, the question is, what variable are we taking the derivative with respect to? So like if you have a function that depends on x and y, are you taking the derivative with respect to x? Are you looking at the changes in x and how it affects the function? Or are you looking at the variable y and how the changes in y affect the function? So we have this concept of partial derivatives. So if u is an open subset of Rn and f is a function from u to r, so think of this as f is a function from Rn to the real numbers, and again f is a real valued function, it maps to the real numbers, then the partial derivatives of f with respect to the first, second, up to the nth variable are the real value functions of n variables which at point x1, x2 up to xn equals x are defined by, so df of dx of the jth variable, so this is, we're taking the derivative with respect to the jth variable, is equal to the limit as h approaches infinity of f of x, and you add a little number h, and then to the jth variable, and then you have all your other variables over h, and this is as the limit as h goes to infinity, minus f of x 1, 2, up to xn. And this formula is really analogous to the formula we used in first year calculus for one variable calculus, and we'll take a closer look at this later in the video. But this is the formal definition, and what it comes down to, what this means is the derivative with respect to the jth variable. That's the derivative with respect to x of j, and we consider all the other variables held fixed. So for example, if z equals cosine of xy plus x cosine of y, and z, just to kind of spell this out, is a function of x and y, it's a function of these two variables, then dz dx, so the derivative with respect to x, is equal to, so now we're going to consider y a constant, and x is our variable because we're interested in how z changes with small changes in x. So that's d cosine x y naught plus x cosine y naught over dx. And the y naught just specifies we're considering this value fixed. And then we're going to evaluate this at x naught. So that's equal to the derivative of cosine x y naught with respect to x is minus y naught sine of x y naught. The derivative of x, now cosine y is now a constant. So x times a constant, the derivative would be just the constant. So that's why we have cosine y here. We evaluate that derivative at x0. So plugging in x0 for x, we get minus y naught sine x naught y naught plus cosine y naught. The second thing we will talk about are tangent planes, because now that we have a derivative, just like in first year calculus, now that you have a derivative, the tangent plane becomes important. So let f be a function from R2 to R. And we can extend this to Rn, but just because we don't want to have a ton of variables, we're going to define this for R2. So it's differentiable at a point x naught, which is equal to x naught y naught, and the plane in R3 is called the tangent plane of the graph at x naught y naught. So z is equal to, this is the tangent plane, z is equal to f of x naught y naught plus df with respect to x naught, and then evaluated at x naught y naught. So this is the derivative with respect to x evaluated at x naught y naught times x minus x naught plus the derivative of f with respect to y evaluated at x naught y naught times y minus y naught. And there's this alternative notation here. So the example is to compute the tangent plane to the graph of z equals x squared plus y to the fourth plus e to the xy at the point 1, 0, 2. So the first, in this formula, we can certainly plug in 1, 0, 2 into this equation to get f of x naught y naught, but we also need the partial derivative with respect to x and the partial derivative with respect to y. So let's do that first. So the partial derivative of with respect to x of x squared plus y to the fourth plus e to the xy. So we're going to consider y a constant. So the derivative of x squared is just 2x, y is a constant, so that goes to 0. Derivative of e to the x times a constant is the constant times e to the xy. And now we need to evaluate that, here, at x naught, y naught. So we're going to evaluate that at 1, 0, 2. Actually, we don't really need the 2. It just kind of gets plugged in there. But anyway, 1, 0, 2. So 1 and 0. So x is equal to 1. So this is 2. Y is equal to 0. So this goes away. So we're just left with 2. df dy of x squared plus y to the fourth plus e to the xy with respect to y. So now x is considered a constant. So this goes away. Here we're going to have 4y to the third. And then here we have x e to the xy, evaluate at 1, 0, 2. So plugging in 1 for x and 0 for y. So here this goes to 0, this goes to 1, and we're left with 1. So the tangent plane, also f of xy, they already told us what at 1, 0 it is, but we can just verify this. So if we have 1 for x and 0 for y, this becomes 1, this is 0, this is 1, so our z value is 2. So our tangent plane is f of x naught, y naught. So at 1, 0, z is equal to 2, plus the derivative of f of x evaluated at x naught, y naught, that's equal to 2, times x minus x naught is 1, plus now our df dy is 1 times y minus y naught, which is 0. So that will give us z is equal to 2x plus y. And like in first semester calculus, near this point x naught, y naught, near the point x naught, y naught, the tangent plane is a good approximation to our function. Next, we have a matrix of partial derivatives of f, and this is a little bit of a change. Here we had a scalar function. Here we are also talking about a scalar function, but now we're not necessarily talking about a scalar function. In our example, for example, we have a function that produces a two-dimensional vector. So here we're talking about a function where possibly we get something in Rn. So f1 is the first coordinate of R2 in this case because it's a two-dimensional answer, and f2 is our second coordinate. So fn would be the nth coordinate of our n-dimensional solution, or what f of xy is equal to. So here, our matrix of partial derivatives will be all the partial derivatives associated with this n-dimensional solution. So here, we start with, on the top line, we're going to start with f1. So the first coordinate, in this case, the x coordinate. So we're going to take the derivative of f1 with respect to the first variable, derivative of f1 with respect to the second variable, all the way up to derivative of f1 with respect to the nth variable. The next line, we're going to go to the second coordinate. In this case, in this example, it would be 4y. In this case, the second coordinate would be y squared x. We would take the derivative of the second function, like the function for the second coordinate, with respect to the first variable, x1, derivative of the second function with respect to the second variable up to the nth variable. And we do that for all of the functions of f. So an example, here we have f of xy maps to e to the xy plus y for the first coordinate. For the second coordinate, f of xy maps to y squared x. So here we have df1 are all the partial derivatives of our first coordinate. So df1 with respect to x and then df1 with respect to y. And the second line is with our second coordinate, df2 with respect to x and then df2 with respect to y. So over here, df1 with respect to x, so y is a constant. So this with respect to x is just going to give us e to the x plus y. Derivative with respect to y, now x is a constant. This will give us e to the x plus y. Now this becomes 1. Derivative of, now we're on the second line, and so we're looking at the second coordinate, derivative with respect to x. So y squared is a constant, so the derivative would be y squared. Derivative with respect to y is 2xy. And then we have this differentiability theorem, which we'll look at in our examples. But if x is open in Rn, so we have a mapping that goes from Rn to R. So it's a scalar function. And let a1 to an be a member of x. So this is where we start. We're mapping from Rn to a scalar. So this is something we're mapping. We say f is differentiable at this vector a if all the partial derivatives of, with respect to a1, a2 up to an exist, and if the function h from Rn to R defined by h of x is equal to f of a plus f of x1 of a, x1 minus x minus a1 plus f of x2, the partial derivative with respect to x2, x2 minus a up to partial derivative with respect to x of xn minus a is a good linear approximation, meaning that the limit as x approaches a of f of x minus h of x, the difference between these two is equal to 0. So they become the same. The h of x is a good approximation for f of x. We'll look at this more in our video. Our second overview slide, I'm sorry the overview is taking so long, but actually the actual video I don't think is that long, but don't hold me to it. Anyway, the next idea we're going to talk about is gradient of f. And the gradient of f is notated with this del. And the del is actually an operator. It operates on functions. So sort of like, addition is an operator on numbers. Del is an operator that operates on functions. And it takes a function, and then it takes all the partial derivatives of the function. So if we have f, then the del gives us df with respect to x1, df with respect to x2, up to df with respect to xn. So in Rn, del of f is a three-dimensional vector, which is the derivative with respect to x, derivative with respect to y, and derivative with respect to z. So our example is if f of x, y, z is equal to x e to the y. So there are three variables, but z doesn't come into play, but that's okay. Del of f, this is the derivative of this with respect to x. So e to the y is a constant, so derivative of x times a constant is just the constant. Derivative with respect to y, and x is a constant, so that'll give us x e to the y. Derivative with respect to z, there's no z term, so that's 0. So this is the del of f, or also called the gradient of f. Sorry, del is the operator, the gradient is the del f. So the theorem is there's a directional derivative, and it's maximized with respect to the direction when u points in the same direction as grad f, and is minimized when u points in the opposite direction. So we're going to talk more about this in a future video, but essentially the gradient points to the direction of maximum change, or direction of fastest change. Our last topic, I'm going to sum up with this one diagram here. So we'll talk about differentiable versus continuous. And this is going to be my summary. I have two theorems. The first one says if we have continuous partial derivatives, that will imply, by this theorem here, that our function is differentiable. If our function is differentiable, just by definition of derivative, that implies that the partial derivatives exist. And you also want to note the converse, going the other direction, statements are not necessarily true. And we'll see this more in the context of our video. So that was a very long overview, but now we're ready to look at each topic in more detail and with more examples. So as I had mentioned, we are looking at differentiation of functions of multiple variables like x1 up to xn. So when we do a derivative, we need to know what we're taking the derivative with respect to. So that's why we have these partial derivatives. I have this picture here. Before we look into this, I think it's kind of useful to remember how we define derivatives in first-year calculus. So we looked at df dx. What we were looking at is how the function changed when we perturbed x just a little bit. So we had a function, and here's x, and we perturbed it by a small amount h. Remember the limit of h, we take the limit as h goes to 0. So it's a very small perturbation in our x, And we want to know, well, how does that affect f of x? And this is, you can also kind of recognize this. So the change in y, that's f of x plus h. So this value minus f of x, so that's this value here, how the change in y, this is the change in y on top, over the change in x, and x just changes by h. And we take this h to go smaller and smaller. So again, we want to know how small perturbations in x change f. That's the same exact analogous thing we have in this long definition when we take the derivative with respect to x of j. So somewhere in this list of all the coordinates or all the variables, x1 up to xn, there's an x of j somewhere in here, buried in here. When we want to define the partial derivative with respect to x of j, we take all the variables as constant except for x of j, and we perturb it by a small value h. And then we subtract our regular f of x1 to x of j is buried somewhere in here up to x of n, and then we divide by h. And then we take the limit as h approaches 0. Again, this here is totally analogous to what we did in first year calculus, and the idea is we want to know how do small changes in x perturb the function in y, or f of x. And you also might recognize this as a slope, right? The change in y over change in x. And of course, this is if the limit exists. And another way, when you actually come to taking, that's like the theoretical, but when you actually come to working with taking partial derivatives, essentially what you end up doing is considering all the other variables here constants, and then x of j is your only variable when you take the derivative with respect to your variable. So for our first example, we have z equals cosine of xy plus x times cosine of y. And z also, I could rewrite this as f of xy just to highlight the fact that we have a function of two variables, x and y. If I want to take the derivative now of z with respect to x, now I'm going to treat y as a constant and x as my variable. So when I have cosine of x times a constant, that's just equal to, and I rewrote it here. When I have the derivative of cosine of x times a constant, that's just equal to negative. We bring out the negative sign. We have to multiply by the constant of xy. So negative y sine of xy. Here, cosine of y, since y is a constant, cosine of y is a constant. So x times a constant, the derivative is just the constant. On our overview slide, we looked at dz dx evaluated at x naught, y naught, evaluated at a point. So in the overview slide, I went ahead and plugged in y naught since it's just a constant anyway. But you could save it and plug it in at the end if you want. But essentially, here I have my minus y naught sine of x y naught plus cosine y naught. So I need to plug in x naught for my x. So plugging in x naught, I get minus y naught sine of x naught y naught plus cosine y naught. And again, you could have just done this and then plugged in x and y naught, and you would have gotten the same answer. And just to say we did, we'll go ahead and compute dz dy, now treating x as a constant and y as our variable. But it's actually kind of the same thing because the derivative of cosine of y times a constant, you bring out your constant. The cosine derivative is negative sine of xy. And here, this is a little different. So now x is a constant, so we just keep our constant, and the derivative of cosine of y is negative sine of y. We're ready to talk about tangent plane now. So I left just this one note or two notes about partial derivatives, and I cleared everything out just to give us some space. So the idea of a tangent plane, we're going to consider a scalar function. And here we're going to talk in particular about R2, but this can easily be extended to Rn. So we're going to let f be differentiable at a point called x naught, y naught. The plane in R3 is called the tangent plane of the graph at x naught, y naught, and it's given by this equation. The tangent plane z is equal to our function evaluated at x naught, y naught. And again, there's many tangent planes on a graph. We're talking about a tangent plane at a particular point. So the first thing we do is we evaluate the function at that point, and then we evaluate the function at the derivative with respect to x, and then we multiply it times x minus x naught. And then we evaluate, again, the derivative of the function with respect to y at x naught, y naught, and we multiply it times y minus y naught. And there's this alternative notation for df dx where you just kind of put a little x underneath. So this here, this little f of x and this f of y stands for df dx, and this stands for df dy. I have this picture here. So the idea is that, in the xy plane, that's your domain, right? Because that's what gets plugged into f, xy pairs. So for every xy pair, you have a height associated with it. And then your graph of, on the z, all these different points, gives you a surface, which I tried to indicate this was a surface with shading. So you'll just have to use your imagination because I'm not a very good artist. But there's this point down here, probably somewhere over here, for x naught, y naught, and you can take the point on the surface and then you can find a plane that just touches that point on the plane, and that's the tangent plane. It's very much analogous to the tangent line when you have f of x equals y. An example, compute the tangent plane to the graph of z equals x squared plus y to the fourth plus e to the xy at the point 1, 0, 2. One comment I'm going to make right off the bat is really they only had to give you 1, 0 at the point 1, 0 because you can figure out z by plugging in 1 for x, 0 for y, and then e to the, that would be 1 times 0. So this would have given me 2. But anyways, just to let you know, this would have given me 2. I could have figured this one out. You could too. And looking at my formula, that's the first thing we want to compute is f of x naught, y naught. So f of 1, 0, which would give us 2. The next thing we need to compute is partial derivative with respect to x and the partial derivative with respect to y. Derivative of f with respect to x, when we have x squared, y to the fourth, e to the xy, so treating y as a constant, derivative of x squared is 2x. This is a constant, so the derivative is 0, and here we get our constant times e to the xy. So this is df dx. df dy now is equal to, now we're treating x as a constant, y is our variable, so this is 0, then we get 4y to the third, and here we get x e to the xy. And now according to our formula, we need to evaluate our partial derivatives at x naught, y naught, x naught being 1 and y naught being 0. So df dx at 1, 0, so we plug in 1 for x, we plug in 0 for y, is that right? 0 for y, and we get 2 times 1, this is 0, this is 0, so we get 2. Over here we plug in 1 for x and 0 for y, this is 0, so we get 1 e to the 0, which is equal to 1. Now I've moved down my formula for the tangent plane and I can plug everything in. Our f of x naught, y naught, we already commented on that, that's 2. df dx evaluated at x naught, y naught is 2 times x minus x naught, so that's x minus 1. And then df dy evaluated at x naught, y naught is equal to 1 times y minus y naught. Y naught is equal to 0, so we have y minus 0. So finally, for our tangent plane, we get z equals 2x plus y. I hadn't planned out my space well, so I had to kind of move everything up here. So I can say as a tangent plane, this equation here is a good approximation to f near the point 1, 0. And in fact, if you evaluate z using the real function at 1, 0, you're going to get 1 squared plus 0 to the fourth e to the 0, which is 2, which is exactly what our tangent plane would give you. And as you expect, so here the tangent plane, right, at that one point kind of touches the point, so you kind of expect that it would be exactly equal. If your function changes a lot, then as you move a little bit away, right, like if you're at this point here, there's a little bit of distance now between the surface and the tangent plane, so you expect your error to get larger as you move away. And this is also totally analogous to what you have in ordinary calculus with the tangent line. Now we are ready to look at the matrix of partial derivatives for function f. As I had mentioned in the overview portion of our video, over here we were talking about scalar functions. Here we were talking about scalar functions. In this portion, we are no longer talking about scalar functions. In other words, now we're looking at vector functions. So f will take something from Rn, an n-dimensional vector, and map it to an m-dimensional vector. So f is a function of n variables, x1, x2, up to xn, and then it'll map it to a vector in ym, so y1, y2, ym. And the thing about this is when it maps it, for the first coordinate, y1, you're going to have a function f1 of the n variables. For your second coordinate, you're going to have a function f2 of the n variables, and up to the mth coordinate, you're going to have a function fm of the n variables. So for example, here if we have f of xy, so we have two variables. So this sort of plays the role of x1 and y plays the role of x2, like looking at this here. So here, this e to the x plus y, this is our f1 function, right? It takes an x and a y, and it produces our first coordinate. So that produces y1. And then our y squared x, this is like our f2. Well, this is exactly our f2 in this. And actually, I wrote x and y here instead of x1, x2, as in this notation. But here, this would be f2, and it takes our x and y's and produces the second coordinate. If we had something that added another coordinate, a comma, and like 2x or something, then that would be our f3. So again, the idea is here we have two dimensions, R2 mapped to R2, but we can extend this to Rn and Rm. So what we can do is we can produce a matrix of partial derivatives, which is exactly what it sounds like. It's a matrix that shows all the partial derivatives that are associated with this function. And the first line is all the partial derivatives of f1, the first solution coordinate. The second line is all the partial derivatives of f2. And the mth line is all the partial derivatives of fm. And so it's df1 with respect to the first variable, df1 with respect to the second variable, up to df1 with respect to nth variable, df2 with respect to the first, df2 with respect to the second variable, df2 with respect to the nth, until you get down to dfm with respect to the first variable, dfm with respect to the second variable, up to dfm with respect to the nth variable. As I had mentioned before, my f1 now is going to be my e to the xy plus y. So df1 with respect to x is, with respect to x, so y is constant, so that's e to the x plus y plus 0. And df1 with respect to y, so x is constant, is e to the x plus y plus 1. And my f2 is now, for my second coordinate, y squared x, so df2 dx, so y is constant, so that's y squared. df2 dy is now 2xy. And then I can plug this into my matrix. So I have df1, the first line is about f1 with respect to x, and then with respect to y. And then my second line is about f2 with respect to x, and then with respect to y. Now we're ready to talk about differentiability, which is our whole next slide. But first we're going to say, let's say x is an open set in Rn. And just say it's a subset of Rn. So f goes from Rn to R, so it's a scalar valued function because it maps to the real numbers, and let a1 to an, that's one of these vectors in Rn that gets plugged into f, it's part of the domain, be a member of x. We say f is differentiable at a if all the partial derivatives of x of a, so this is the partial derivatives 1 through n, exist, and if the function h, Rn to R, defined by, and we use this tangent approximation, is a good linear approximation of f near a, meaning the difference between f of x and h of x, h of x being this tangent approximation as x approaches a, is equal to 0. So how good of an approximation it is also an indication of differentiability. Now we're ready to go on to our second slide of topics. The next topic is that of the gradient, which can be notated as grad f, or this del f. So this is gradient of f is equal to the list of partial derivatives. In R3, that looks like df dx in the I direction, df dy in the j direction, and df dz in the k direction. And you can just simply write this as a coordinate df dx, df dy, df dz in 3 dimensions. So our example is here we have f of x, y, z is equal to x e to the y. So there's no z in this function, but it is in R3. So the del, the gradient of f, is equal to the derivative of this with respect to x. So e to the y is just a constant. Derivative with respect to y, that's x e to the y. And with respect to 0 is just 0. We have this theorem that says the directional derivative is maximized with respect to the direction when u points in the same direction as grad f. We have a whole nother section of this chapter devoted to the gradient of f, and the idea is that the gradient of f points the direction of fastest change in f, and it's minimized when u points in the opposite direction. I'm going to use this tangent plane drawing again. So the idea is we have this surface, right, that is what our function produces. And at a particular point, let's say we're here, this function, if you go this direction, it looks like you might stay constant. If you go down this, it looks like your function might start decreasing, right? It kind of looks like in this direction, things are lower. If you go in this direction, it looks like things are increasing. Well, if you want to know exactly if you're standing at this point and you want to climb the hill, so to speak, you want to go up as fast as possible, you want to increase your values of f as fast as possible, you will go in the direction of the gradient. That's what this means. And as I said, there's a whole nother section of this chapter devoted to gradient. So we'll look at this more, but I guess it's mentioned here, so we mention it here too. Next, we will talk about differentiable versus continuous, and we're going to motivate our discussions with this example. F of xy is equal to 1 if x equals 0 or if y equals 0, and it's equal to 0 otherwise. So in other words, everything is in the xy plane, this yellow plane here, and actually it goes, forward and back. It's not just the positive xy plane, except at, let's see, when x is equal to 0 or y is equal to 0. So along the x equals 0 axis, that's over here, then all of a sudden we have these values that pop up at value 1, and then at y equals 0 we have the values that pop up at f of z equals 1. So since f is constant on the x and y axis, right, where x is equal to 0, that's along the y axis, f is constant, it's equal to 1. And on the where y is equal to 0, that's along the x-axis, we have f is equal to 0. So the partial derivatives, so if you're looking at the change in f with respect to x, holding y constant, so y constant, that'll be along here, the derivative with respect to x is equal to 0 because there's no change. It just stays constant at 1. So there's no change, so that's equal to 0. We can evaluate df dx at 0, 0, and it's 0. Also df dy, all along this axis, there's no change as we change y. So, right, it stays constant at 1. So df dy at 0, 0 is also equal to 0. So we can take these partial derivatives, but we can't say that f is continuous at 0, 0, because if we look at the limit, right, when we're approaching at something, let's just say from this direction, you have to be able to approach from all directions, but as you approach from all these directions, it looks like f is equal to 0. It's in the plane. And then all of a sudden there's this jump over to 1. So we can't say that we cannot say the function is continuous at 0, 0, because the limit of f of xy as xy approaches 0 from all these other directions does not exist. So f is not differentiable at 0, 0. So you can't take a derivative of f. We're not talking about partial derivatives, but technically f is not differentiable at 0, 0 because the limit as we approach from different directions is not, it doesn't approach the value 0. There's this jump. We had this definition of differentiability on our first overview slide, which I sort of glossed over, and it has this test where you can look at h of x, kind of this tangent sort of formula, and see that the difference as x approaches a, that the difference is equal to 0, or in the limit they are equal. But this is sort of difficult to apply, so we're going to have a couple of other theorems that are going to help us determine if things are differentiable. So the two theorems I have to help me with this is, first, let f go from Rn to Rm. If f is differentiable at a point in Rn, then f is continuous. So in other words, differentiable implies continuous. The second theorem, suppose the partial derivatives of f all exist and are continuous, then f is differentiable. So partial derivatives imply differentiable. And actually, I should have put continuous here, but I have this in my summary. So continuous partials implies differentiable. This is my theorem with an asterisk. And then differentiable implies partial exists. That's just the definition of differentiable. And we want to note that the converse statements are not necessarily true. If the partials exist, it doesn't mean differentiable, and that's exactly what this was about here, this example. An example of how we apply this theorem goes to this function f of x here. We want to show that f is differentiable at all points x, y not equal to 0, 0. So I cleared out some space to make my room for my example. And I'm going to start by taking the partial derivative of this with respect to x. So I'm going to consider y a constant, and since this is a quotient, I need my quotient rule, so that's the denominator times the derivative on what's on top, considering y a constant. So that's going to be y e to the xy minus sine of x, and then minus what's on top, cosine x plus e to the xy times the derivative on what's on bottom, the denominator. So that's going to be my 2x. And why do I have an, oh, because this is a minus. And then over the denominator squared. Similarly, I can take the partial derivative with respect to y. I can see now if I plug in, these derivatives are continuous everywhere except at x equals 0 and y equals 0. This is an and, not an or. So what that means is, by my theorem, I have continuous partial derivatives. Therefore, f of xy is differentiable by the asterisk theorem. Now that we've gone through all of our material, we'll look at some extra problems. The first problem is to find the derivative of the function with respect to x when f of xy is equal to xy over square root of x squared plus y squared. Since this is a quotient now, I'm going to take the derivative holding y constant, so with respect to x, and I'm going to use the quotient rule, which is the denominator times the derivative on what's on top. So x is our variable, so that's going to be just our constant y, minus what's on top times the derivative of what's on bottom. That's 1/2 square root of x squared plus y squared. Derivative would be 2x, all over the denominator squared, which is x squared plus y squared, and then I simplified it here some. Our next example problem is to calculate the matrix of partial derivatives for this function here. And the matrix of partial derivatives is the first function, this first variable here. We take the derivative with respect to x, with respect to y, and then we're with respect to z. And then we take our next function and calculate the derivative with respect to x, with respect to y, and with respect to z. So again, starting here for this first line, derivative of this with respect to x, so cosine y is just considered a constant. So x times a constant, the derivative of that is just a constant. And then z goes away because it's just a constant. Next, we take the derivative with respect to y. So now we have x, and the derivative of cosine y is minus sine of y, and derivative of z, which is just a constant, is 0. Last, we take with respect to to z, and this is a constant, so it goes away, and then we have 1. On the second line, we look at our second coordinate. We take it with respect to x, we get y. With respect to y, we get x, and with respect to z, we get 0. The next problem, given f of x, y is equal to x squared y squared if x, y is not equal to 0 and 0 otherwise. We want to calculate the partial derivative with respect to x, the partial derivative with respect to y, and then answer is f differentiable at 0, 0. Here I have the derivative with respect to x. So treating y as a constant, I get the derivative of x squared is 2x times the constant y squared, and that's when xy is not equal to 0, and the derivative of 0 is 0. With respect to y, again treating x squared as a constant, so I'm going to get my 2y and my x squared, and then I look at this, so the derivative of x, f with respect to x at 0, 0 is equal to 0. So looking at this theorem here, if we have continuous partials, then it's differentiable. But looking at this, our partials are not continuous. So this theorem doesn't apply. And since x, y going to 0, 0 does not exist, it is not differentiable at 0, 0. This next problem is to find the equation of the tangent plane of the n-dimensional paraboloid in Rn plus 1 given by x of n plus 1 equals x1 squared plus x2 squared up to xn squared at the point 1, 2, 3 up to n. And just to note, because this notation is a little different, so this is like x to the n plus 1, it sort of plays the role of z. And it's a function of these n variables, so f of x1, x2 up to xn, and the function itself is x1 squared plus x2 squared up to xn. Sort of the idea is in the same way usually you write your function f of xy, but when you have a bunch of them, like n of them, not more than 2, you just call them x1, x2. So in this point, z, instead of writing z, you just call it xn plus 1. And so for example, if n is equal to 2, then x3, which we'll call z, is equal to x1 squared plus x2 squared, and we can call this x1x and this x2y. So you have the familiar paraboloid shape. I have copied our equation for the tangent plane, and remember this is to go from R2 to R, so it's only two-dimensional, so we can kind of extend that. Instead of just going z equals f of x dot y naught, now we have f of, and now our x naught y naught is given to us as 1, 2 up to n, plus df dx1, and then we plug in our x naught y naught, which is 1 through n, x1 minus 1, x naught is 1, plus df dx2, and then our given point, 1 through n, and then y, which is our x2, minus our second point in our given point. And then we're going to keep doing this all the way through df dxn, because we have n variables. When I look at this formula, the next thing I need are the partial derivatives, df x1, df dx2 up to df dxn, which is actually the gradient of f. So I'm just going to write that. I mean, you don't have to realize that. You can take each of them separately, but I like using the gradient. So the del of our x1 squared, x2 squared up to xn squared, or here's our function, is equal to partial derivative with respect to x1, df x1. All of these go away because they're constant, and you get 2x1. Partial derivative with respect to x2, all of these other things are constant, so you're just left with 2x2, all the way up to xn, which will get 2xn. And from our theorem here, since the partials are continuous, right, 2x1 and 2x2, there's no asymptotic behavior or strange jumps. These are just lines, actually. So since the partials are continuous everywhere, so continuous partials imply differentiable. So f is differentiable everywhere. I brought down the equation of the tangent plane from here over here, and I did start filling some things in. I kept the f of 1, 2 through n here, and then I have my df1 x1 evaluated at 1, 2 up to n. Oh, I didn't change anything. And then x1 minus 1. Okay, never mind. I'm sorry. I didn't change anything here. I just brought it down so I can see more easily where the rest of the stuff is going to come from. So my next line, my f of 1 through n, so if I plug this in, that's going to be my 1 squared, my 2 squared, up to n squared. So this is my f of 1 through n. My df dx1 I have here. It's the first part of my gradient is 2x1, and I need to evaluate it at the point 1, 2 up to n, and then multiply times x1 minus 1. So again, this part of the gradient is derivative of f with respect to x1. Again, all of this is constant, so it goes away, and you're just left with 2x1. Over here, I have the df2 of x2. So that is 2x2, and I need to evaluate it at my point 1 through n, and I'm going to multiply by x2 minus 2. And I do this all the way up to dfxn. That's my 2xn evaluated at my point, xn minus n. And then finally plugging everything in. Okay, so I bring down my my 1 squared plus 2 squared up to n squared because I don't want to do the math here. So now I'm going to plug in my point 1, 2 up to n. So I want 2 times my first variable, so 2 times 1. So that's just going to give me 2 times my x1 minus 1. Then I have 2 times my second variable, that's 2 times 2. So that's 4 times my x2 minus 2. Up to, then this is 2 times my nth variable, so that's just 2n times xn minus n. Also, you notice I have this gradient of f at 1, 2 through n. So in other words, I plug in 1 on this one, 2 on here, and on here, and I get the 2, 4, 6. I get the kind of the coefficients which come, I could have just popped them in right from here. But however you want to do it. But here is the equation, the final solution. That doesn't sound so good. This is the solution of, or this is the equation of the tangent plane. Those are my examples. So now we can review what we have covered. So we talked about differentiation of functions of several variables. We talked about partial derivatives. In effect, basically when you have several variables in a function, when you take a derivative, you have to know with respect to what variable, which variable you're looking at the changes. All the other variables are going to be held fixed. So partial derivative of f with respect to the jth variable is the derivative with respect to the variable v sub j. So we treat the jth variable as a variable, and all the other x sub i's are held fixed. So we have our simple example with z equals cosine of xy plus x cosine of y, and instead of z I could have said f of xy. The derivative of z with respect to x, so treating y constant, and also this x naught y naught means after we take the derivative we're going to plug in x naught and y naught in. We're going to evaluate it at a point x naught y naught. But let's just take the derivative here. So the derivative of cosine x and y plus x cosine y is equal to treating y as a constant. Cosine x would give us negative sine x times our constant. So that's negative y sine of x y. And then x cosine of y. So if y is a constant, then cosine of y is a constant. So x times a constant, the derivative of x times a constant is just equal to the constant cosine of y. Next, we look at the tangent plane. So if we have a function that goes from R2 to R, and we did an example for Rn to R. So it's a scalar function, multi-variables into a scalar. Then the plane is called the tangent plane at the graph, and the formula z is equal to our function. So it's the tangent plane at a point, because at different points you're going to have different tangent planes. So that's equal to the function evaluated at the point times the partial derivative with respect to the first variable evaluated at the point times x minus your x naught plus your partial derivative with respect to the second variable evaluated at the point times y minus y naught. And there's this alternate notation which essentially is just whenever you have a derivative with respect to x, you just call that f and then a little subscript x. df dy would give you f little subscript y. We have an example. Compute the tangent plane of the graph z equals x squared plus y to the fourth plus e to the xy at the point 1, 0, 2. So first, our f of x naught y naught, we can plug in 1 and 0, and we get 1, we have 0, we have 1, so that's 2. That's this point here. Next, we need the partial derivative with respect to x, and then we evaluate it at 1, 0. So partial derivative with respect to x, treating y as a constant, that would give us 2x. Y, this is a constant, so it goes away, and then e to the x times a constant, the derivative would be y e to the xy. We evaluate that at 1, 0, plugging in 1 here, 0 here, we get 2 is our answer. So this is this 2 times my x minus x naught. So that's x minus and x naught is equal to 1. Plus, now we need the partial derivative of f with respect to y. So treating x as a constant, so this goes to 0, we have 4y cubed, and here we have x e to the xy. We evaluate that at 1, 0, and we get 1, so that's this 1 here, and then multiplied by y minus y naught. So that's y minus y naught is 0. So this is the equation of our tangent plane. And as the tangent plane, it's a good approximation to f near the point x naught, y naught. Next, we looked at the matrix of partial derivatives of f, and this assumes that f is not a scalar function, but a vector function. I had to make this smaller to fit this in. So in other words, f goes from Rn to Rm. So f takes an n-dimensional vector and produces an m-dimensional vector. This f1 gives you your first coordinate. So it takes the n variables and gives you a first coordinate in Rm. F2 takes the n input vectors, or input takes your Rn and then gives you the second coordinate of Rm. And then your Fm, your last function, takes your n variables and gives you your last coordinate. So this first line is all the partial derivatives of f1. So this is df1 with respect to the first variable, df2 with respect to the second variable, all the way up to df1 with respect to the nth variable. The second line is for the second function that gives you the second coordinate in Rm. So this is df2, dx1, df2 with respect to the second variable, df2 with respect to the nth variable, all the way down till you get to the mth function, all the partial derivatives. And this was our example. F of xy is equal to x e to the x plus y, and then y squared plus x. So in this case, this is f1 that gives you your first coordinate of R2, and this is your f2. So the first line of your matrix of partial derivatives involves your f1 function, the function that gives you the first coordinate. So df1 with respect to x, so now we treat y as a constant, and we get e to the xy. df1 with respect to y, treating x as a constant now, we get e to the xy plus 1. The second line has to do with the second coordinate of your answer. So df2 with respect to x is equal to y squared, and df2 with respect to y is equal to 2xy. Then last we talked about differentiability, and we have this, basically it's saying that we say something is differentiable if the partial derivatives exist and that your function, kind of your tangent line sort of function, is a good approximation or sufficiently good. We talked about gradients, which is preceded by this del, this upside down triangle operator. So gradient of f is all the partial derivatives with respect to the different variables. And now, again, we're talking about f going to being a scalar function. So our example is f is equal to x, y, z. So the gradient of f is the partial derivative with respect to the first variable, partial derivative with respect to the second variable, and partial derivative with respect to the third variable. So with respect to x, we get e to the y. With respect to y, we get x e to the y. And with respect to z, we get 0. And we have this theorem here, although it's going to be explored later in the chapter, that the directional derivative is maximized with respect to the direction when u points in the same direction as the gradient. In other words, if you want to increase your function the fastest, you'll go in the direction of your gradient. So the gradient will point you in the direction to go. Again, that's something we'll cover in a future video, in a future chapter. We talked about differentiable versus continuous, and this is the summary here. We have this starred theorem that says if we have continuous partial derivatives, then our function is differentiable. And if our function is differentiable, we can always, the partials will exist. The converse, so you can't read the arrows the other way. Differentiable does not imply continuous. And we had our example here, which I'm kind of tired, so I'm not going to do that, but you could take a look at it. By way of review, I have 3 problems for you to try, so I suggest you pause the videos, give the problems a try, and then come back and I'll have solutions for you. The first problem is to calculate the gradient of e to the xy plus sine of xy. The second is find the equation of the tangent plane to the surface z equals x squared plus 2y squared at the point 2, -1. And the last problem is f of xy equal to x squared minus 3xy plus 2x minus 5y differentiable. Here are my solutions. And that's it for this video. Thank you for watching.